طيب بسم الله الرحمن الرحيم. So we talked last time about the two techniques for routing. We talked about a link state routing protocol, which is Dijkstra, which maintains a global view of the entire network through the link state database. And then we use Dijkstra to calculate the shortest path tree from one source to all the other destinations. We also talked about distant vector routing protocol or distant vector routing technique, which is Bellman-4. So Bellman-4 does not maintain a global view, and it calculates the distances accumulatively through some decentralized technique. One thing we talked about in distant vector routing protocol is that if we have a coast change in one of the links, the routers which are directly connected to this link will detect it first, and then based on that, the technique will be triggered to try to convey or spread the information about the change of this price to the entire network in a decentralized fashion. One characteristic related to that is, well, good news travel fast, and we proved that last time, that if a link changes its price to a better price, chances are this new price will travel through the network in a fast way. And that's basically because of the fact that the nodes will find that this is a better link price, and it will not really change the routes for the links. For the routers, in which case the routers will maintain their connections, and it will only update the price based on the new price of the link. So today we want to see the other case when the link price, becomes worse, and we need to prove that, unlike good news, which travels fast, the bad news, they travel slow, and we need to know how slow, and we need to analyze that and be able to calculate the number of iterations required to convey or to spread the news amongst the network nodes for this new price. So pay attention to the fact that here we're talking about a very simple network of 3 nodes. We're not talking about a very large network. But as we will see, still, I mean, the link price, the worst link price, will, update its way through the network in a very, very slow way. It requires 44 iterations. So we need to see why this happens. So in order to see why this happens, at time 0, we need to know exactly the distances that are stored in node Y. So node Y here, assuming that node Y is the node that will get triggered when this link price becomes worse, right? So at time 0, node Y has certain distances, okay, which are coming from Z and from X and from its own self. So Y knows that the distance between Y and Z is 1. That's no-brainer. Y knows that the distance between itself and X is also 4, right? And now it's becoming 60, right? So, but the distance is actually 4, or it was 4, right? So this is the most important part. Y knows that the distance between Z and X is what? Is 5, which is through Y itself, right? So it was 5. This is the most important part, okay? Again, remember that these nodes do not maintain a global view. So Y does not know that the distance between Z and X is through Y. Y doesn't know this information initially, okay? So now Y needs to calculate the new price for from Y to x, right? So when y calculates the distance between itself and x, this distance is actually the minimum, of course, of node, the cost from y to x, okay, or the distance between, the cost from y to z plus the distance between z and x. Okay? So, of course, this is actually simply the minimum of 60, which is the cost between y and x, or the distance, the cost between y and z, which is known by y, of course, which is 1, plus the distance between z and x. What is the distance between z and x? It's? لا.
Z and X.
That's the problem بقى. It's what? لا, what is the distance between z and x? What is the distance that y has about the distance between z and x? 5. Right? So this is the distance that y has about z to reach to x. Okay? So in that case, this will be 6. The minimum is 5 plus 1. Right? So the minimum is 5 plus 1. So which means that y knows now that the shortest path to x is no longer by 4. The shortest path to x is in fact through z. فهمنا دي جت ازاي؟ This is very important. Okay? See بقى the ping pong effect that will happen now, because y now knows that the distance between itself and x is 6 and it's through z, right? So the price to x is now changed, right? So in that case, y will have to send the distance between y and x to z. So now z will try to calculate the distance between z and x, which is the minimum of the cost between z and x, right? Or the cost between z and y, right? Plus the distance between y and x. صح؟ تمام كده؟ So what is this? So the cost between z and x is 50, and the cost between y and z is 1, and the cost between y and x is 6. So this will become 7. So the new distance between z and x is now 7, right? Which is different. صح? So in that case, z will inform y in a different iteration. Okay, so we started from 6. Okay, and y informed z that the distance between y and x is now 6. So z calculated the distance between itself and x based on the distance that it received from y in another iteration. كل دي different iterations. Okay, طيب. So now what will happen? Okay, so now the distance between z and x is 7. So y will calculate the new distance between itself and x. And this is based on the minimum of two things. The cost between y and x, which is 60. صح? Or the cost between y and z, which is 1, plus the course between Z and X, which is 7. So now it becomes a 8. So we'll continue in this ping pong effect, right? That's for route update. Huh? This is for route update. So for route update, we need to calculate when will the shift happens and the steady state will be achieved. Okay? We need to know when will the shift happens and the steady state will be achieved. This, in fact, will happen when the cost between Z and X will become a 50. Okay? So when the cost between Z and X becomes 50 after different increments, right? So the cost between Z and X becomes a 50. So now we need to calculate the cost between Y and X based on the fact that the cost between Z and X is 50. So this is the minimum of the cost between Y and X, which is 60, right? Or the cost between Y and Z, which is 1 plus 50. So now this cost between Y and X is 51, right? But still it goes through Z. So Y will send that new distance to Z, right? Type. Until now the steady state did not happen. Okay, so now after 44 different iterations, now the cost between Y and X becomes 51. So now we need to calculate the cost between Z and X. And this happens at node Z, right? So node Z will say, okay, so the cost between myself and X is either the cost between Z and X, or the cost between Z and Y plus the distance between Y and X. So what is this? 51. And what is this? It's 1. What is this? 50. So now this cost will become 50. Okay? So now Z will not route through Y. Z goes directly to X. So now the cost between Z and X will be 50. Okay? So the cost between Z and so the cost between Z and X is now 50, and X will send back to Y. So Y will calculate again the cost between Y and X. What is that distance? It's the minimum of, again, 60 and 1 plus 50. So it will be 51, which is still the same, right? خلاص, everything will be stable. When does this happen? When did this happen? When Z started to realize that it should not go through Y and it should go directly to X. Okay? But before this happens, we had this ping pong effect, okay, which is again based on the fact that we do not maintain any global view here. Okay? Z does not know that the price that it has to reach to X is in fact through Y, yet it actually informed Y, right? And Y does not know that the distance it has to X is actually through Z, and it informs that. Okay? So this is the problem. And again, this problem happens because none of them knows that they actually route through each other. So this is the effect of, we call this problem count to infinity, by the way. This problem is called count to infinity, okay? And this is the effect that happens for route updates. So we started from 6, and we had this ping pong effect until we reached to 50. That's why we had 44 different iterations. Okay? Let's see about the effect on the data, because all of this is regarding route updates. Okay? So during this ping pong effect, what will happen في هنا حاجة تخليني أقدر كان بيبقى في اكس هنا مش عارف راحت فين. ما علينا. ايوه Okay, so during this route updates, during these 44 iterations, what will happen if I have a packet with a destination X that comes here at Y? This is actually data بقى. Data is coming to node Y, and the destination is X. So what will happen? Y knows that the shortest distance between it and X is actually through Z, right? So Y will send it to Z. So the packet will come here. Okay? So Z knows that the shortest distance to X is through Y. Right? صح? This is during this ping pong effect. So Z will send it to Y, and Y will keep sending to Z until the route updates settle down. And that may take, by the way, minutes. Okay, so we'll see the frequency of these route updates when we start to talk about Ripple. Okay, so the effect on the route updates is that we have 44 iterations, and these iterations might be as slow as 1 every 30 seconds. This is the case for RIP, مثلا, Routing Information Protocol. These route updates, they take 30 seconds. Okay? So, يعني multiply by 30 seconds, multiplied by 44, so you can imagine the amount of time where this network becomes unstable. Of course, that's not acceptable, and routing protocols, they have to resolve this issue. So the way that they resolve this issue is through what we call a Poisson reverse. In fact, they call it split horizon with Poisson reverse. This is what we have studied in Network 2, Fruit, if you remember. Okay? So the way that this Poisson reverse works is that if Z knows that this distance is in fact coming from Y, okay, then it should not inform Y about its distance to X. And in fact, it should inform Y that the distance to X is infinity. Because this is what caused this problem. If I know some information from you, I should not flip it back to you. Okay? Because the main source of this information is you. So if Z knows that this distance, the distance that it has for X is coming from Y, it should inform Y that the distance to X is infinity. Okay? So this is the split horizon with Poisson reverse. So this is what this is the poison. We call this poison. Yeah. Okay? So we poison the route back when we send it to Y. So now, how can this solve this particular problem? If Y knows that, خلينا نمسح دي. مش عارف ليه هو بطيء جدا. Okay, if y knows that the distance between z and x is now infinity, so we go back to calculating the distance between y and x, which is the minimum of the cost between y and x, which is 60, okay, or the cost between y and z, which is 1 plus infinity. So in that case, y will say, okay, so it's 60. So I should go directly to x. Of course, that's not the shortest path. We know that, right? But that's what y will say. Remember, now y sends directly to x. So it's not through z. So y is now allowed to send to z its distance to x. صح? According to the split horizon rule, okay, y sends directly to x. So I'm not sending through z, so I should inform z about my price to x. That's no problem, right? So now, in another iteration, z will say, okay, so I need to calculate my distance to x. صح كده? So this is actually the minimum of the distance between z and x, which is 50, okay, or the distance between myself and y, which is 1 plus 60, right? So what is the minimum? It's a. Remember, we have reached that state after 43 different iterations last time to force z to go to x directly, okay? So now we have reached in one stage, we forced z to realize that it should send to x and not through y. So by doing this, we have saved 43 different iterations, okay? And now z does not route through y, so according to the split horizon rule, this distance should be reported to y. There's no problem. صح؟ مظبوط؟ تمام. So y will say, z will say, okay, so I should send the distance between me and x to y. That's no problem. So y will say, okay, so now I need to calculate my distance to x, which is the minimum of 60 or 1 plus 50. So it's 51. So in 2 iterations, we solve the problem just by using this split horizon rule. So split horizon was posed in reverse, solved the problem, which is good news. The bad news is, empirically, split horizon was posed in reverse does not, in fact, solve the problem in all cases. And in very complicated networks, even the split horizon rule may not solve the problem 100%. It reduces it, but we cannot claim that it eliminates the problem completely. ماشي? So it's partially good news. That's why for count to infinity, rep, as we will see, rep, in fact, allows count to infinity to happen in some cases, okay? And it considers that the distance 60 is in fact equivalent to infinity. So if for any reason that ping pong effect happened, طبعا it doesn't happen between only 2 nodes in complicated networks, it may happen بقى through some loops وحاجات كده يعني. So even if that happens, if we reach to 60, we consider that infinity. خلاص. So we consider 16 as infinity. That's why the maximum number of hops in any rep network is supposed to be 15, not 16. The maximum valid number of hops for rep networks is supposed to be 15 and not 16. Okay? So 16 is considered infinity, which means that the link is disconnected. So if you ever reach to 16, that means that the link is disconnected. ماشي. Any question here? طيب, so comparing بقى link state with distant vector when it comes to message complexity. Message complexity معناها ايه؟ The complexity of the number of messages I need to send in the case of link state versus distant vector. So in the case of link state, we need to report the state of every link in the network to every node in the network, صح? Okay, so it's basically O of n, which is n is the number of nodes, times E, which is the number of edges. Edges are the lengths, and n is the nodes. So we need to report all the states of all the lengths to every single node in the network. Okay? So the complexity of the number of messages is O of n times E. In fact, this is not the communication cost. Okay? The communication complexity is even more than this. Why? Because every state of an edge is flooded through the network, which means that the state of one link gets transferred over multi-hop. So every state of every link needs to go through multi-hop to reach to all the nodes in the network. So the communication complexity is even more than this. We cannot really calculate it exactly, ولكن it's even more than this. Type. For distant vector, we don't know. We don't know because it's each node reports the vector of distances between it and all its neighbors, right? And we don't know how many items in its routing table. That depends on the number of neighbors that it has, and it depends, that it reports these distances for one hop, and when it goes to the other node, it reports its distance to the next one, and so on. So we cannot have an estimate of the number of messages. That it depends on many things. So we cannot really find the real complexity. But we know that we need to report these vector of distances regularly and periodically. Okay? Or in certain cases, when an event happens, we need to send it immediately. Sometimes for some routing protocols like EIGRP supports immediate or event-triggered updates, okay? In addition to the periodic updates sometimes. So it combines or it mixes between the periodic updates and the event-based updates. Okay? Type. When it comes to the speed of conversions, only the speed of conversions, this is by directly from Dijkstra's algorithm that we talked about last time. And for Dijkstra's algorithm, we said that we have different iterations, and for each iteration, we have to remove one node and put it in n dash, right? Which means that the number of calculations for the distances always reduces by 1, right? And we calculated that to be O of n squared, right? So that's so the complexity for Dijkstra's algorithm is in fact constant, and it's fixed because again you have the entire link states in the link state database, and you run Dijkstra's algorithm once and for all, right? For distant vector, again, we don't know because this is an iterative algorithm and we have no idea when we will reach to the conversions. The state of conversions is not really realizable easily. Okay, so for any iterative algorithm, it's always very hard to calculate its complexity because, especially in a decentralized way, because we don't know exactly when we will reach to the steady state. Okay, so that's why again for distant vector routing protocols we don't know the complexity exactly, but we know that it's the complexity per iteration is pretty small. Per one iteration is pretty small because you report the vector of distances to all your neighbors, and sometimes use multicast to do that. So it's a very simple iteration. And actually the amount of updates that you report is only the distances known to you, which means you report whatever in the routing table, you report it to the neighboring nodes, and that's it. Okay, so it's not very complex, but we don't know when the steady state will happen. So you may have to report these vector of distances all the time. And that's why, as I showed you last time. So in terms of, this is the time, and this is the number of messages, okay, through route updates. For link state routing protocol, at the beginning, we have to do flooding, صح? So flooding will have to spread to the entire network, so that the number of messages through route updates at the beginning is very, very high. But then, once we reach to the steady state, and we know how to reach to the steady state, then it drops suddenly, okay? And we only report if a link changes its course. That's it, or it becomes disconnected, okay? So after you reach to the steady state, you only report the events only. Okay, we only report the events. For distant vector, however, we find like it's like this. It's much less, right? Because again, we report vector of distances to the neighboring nodes. That's it. Okay, so it's much less in terms of the frequency of the route updates. But this less frequency is continuous, because we don't know when the steady state will happen. In some cases, but especially in EIGRP, they try to actually do something about it. So you have to keep the periodic updates for a very long time, and then you can reduce it a little bit by using a mix between the periodic updates and the triggered updates. Only EIGRP does that. REP doesn't do that. REP only supports periodic updates, and it runs all the time. EIGRP tries to be a little bit smart. مفهوم الكلام ده ولا صعب؟ مفهوم؟ تمام. طيب. So this is a quick comparison. Now, so when it comes to robustness هنا is against possible errors. So we need to see. So a node can advertise incorrect link cost. So if a router مثلا malfunctions, and by malfunctions here, I mean the router itself started to work in a funny way, and it reports some wrong course, or there is some compromise that happens to one router. One router is attacked, and it reports some wrong costs about some of the links. Okay. So in link state routing protocols, the node will advertise this incorrect link. So what is the effect of advertising a wrong state about one link, مثلا? Okay. So it turns out link state protocols are more resistive to these kind of problems. Why? Because again, the incorrect link state will be flooded, صح? Will be flooded, مظبوط. And each node will have a link state database which might have one link with wrong state, صح? طيب, what is the effect of this? The effect of this, I argue that the effect of this will be localized, and it may not have an effect for certain parts of the network. Why? Because a node will realize that if this link cost is high, it will find a different route through Dijkstra's algorithm. It will find a different route, and it will go around this link. ماشي؟ طيب. But there will be some effect, definitely. But the effect will be a little bit localized. So let's see if this happens for distant vector. For distant vector routing protocols, this wrong cost of the link, okay, will be traveling to other links in the network, which will be used to calculate distances right? And these distances will have to be reported to the other nodes, صح? Which will be dependent on these coasts to calculate their distances to the. So what I'm trying to say here is that this wrong information will propagate its effect, and the error effect will be exponentially increasing. مفهوم ليه؟ يعني when I say مثلا to Ahmed, the distance between me and X is now 3. فأحمد هياخد الانفورميشن دي ويستخدمها في حاجات تانية وهو he doesn't know that this is a problem. There is a problem with this. فأحمد may calculate something and will send it back to Nirma, and Nirma will calculate something and send it back to, and so on and so forth. So the effect of the error will propagate and will start to increase, right? So link state, because it maintains a global view, okay, Dijkstra's algorithm may in fact find different ways to go and bypass the link with the wrong state, and it may not have any effect. But for distant vector, I have no other choice, because the error will be accumulating through the distant reporting to the other nodes, right? And the error will propagate through the network and will have drastic effect in that case, okay? So this is not to say that link state is the best and it's better in everything, right? Why? Because, I mean, we have seen that route updates, for example, are less complex. Not only that, Dijkstra's algorithm is indeed صح, it's O of n squared, which is not bad, but in order to have Dijkstra's algorithm to work, I need to maintain a link state database with all the global view of the entire network. I don't have to do that for distant vector. So that's a storage complexity, okay, in addition to the computation complexity. تمام? So يعني we cannot argue that one is the best and the other one is bad in everything. So there is always a pros and cons for each one. And that's why يعني we'll start to talk quickly about one example for a protocol that uses distant vector, one example for a protocol that uses link state and so on. ماشي؟ طيب. Hierarchical routing. The problem for hierarchical routing here, the idea is that we cannot really assume that the entire internet, okay, can be in fact a domain with that runs مثلا Dijkstra's algorithm or runs link state or something like this. The internet is really, really complex, right? So we cannot afford the fact that we can consider the internet as one domain, because indeed it's not. One reason is for scalability. So we cannot afford the fact that route updates, okay, will have to travel through the internet, the entire internet. Can you imagine that مثلا for link state, and then I need to flood the link states of the entire links on the internet to the entire nodes on the internet? Of course, that's not feasible, right? Another problem is that indeed even the internet is not designed to have one single domain, because naturally every internet service provider has its own control over its own infrastructure, right? So within their own infrastructure, they may need to have full control, and they may need to run مثلا rep, while in another infrastructure for another ISP, they may run OSPF, okay? So they have control over their infrastructure, so we cannot force them to say, no, we have to have rep in everywhere. ما ينفعش, we cannot do that, right? So hierarchical routing came to solve that problem. So we will have inter-domains, we will have multiple domains in the internet, okay? Every domain will have its own control for their infrastructure, and they may be allowed to run whatever routing protocol they deem appropriate. يعني ممكن أريدو they select to use OSPF, Vodafone they run rep, doesn't matter, right? But we need to have like some inter-domain communication way, okay? So that's what hierarchical routing is made for. So hierarchical routing made to solve the scalability problem. So we will run the distant vector or link state routing in specialized domain locally, but we have domain-to-domain communication, which is what we call inter-domain routing, okay? So hierarchical routing here supports two types: domain routing and intra-domain routing, okay? So hierarchical routing here aggregates router into what we call autonomous system. So autonomous system is a group of network devices under the authority of one single organization or one single entity. أنا مش عارف ليه لما بقول الحاجات دي يعني الناس مش فاكرة أي حاجة من نتورك 2 لأن الكلام ده كله اتشرح في نتورك 2 المفروض. So autonomous system is a group of network devices under the control of one single authority or one single entity. Okay? So we may have autonomous system مثلا to represent, this is Ooredoo. Autonomous system here to represent, this is Vodafone. Okay? And so on. So and within each autonomous system, this entity will have full control. These are group of routers and switches. These are group of routers and switches, right? And within the autonomous system, they can run any of the techniques we talked about, link state or distant vector. Sometimes they can run both, by the way. There's nothing that can stop them from running both at the same time. Okay? So each of these routers, they will have their routing table to perform the forwarding based on the knowledge inside that autonomous system only. So all route updates that we talked about will be only within the domain of the autonomous system. بس. ماشي كده؟ And within the domain, we have what we call intra-autonomous system routing, which can be done using RIP, OSPF, via GRP, or any of the طبعا as we will see, RIP مثلا uses distant vector, OSPF uses a link state, and so on. ماشي? So within the autonomous system, we can run one of the intra-autonomous system routing techniques like Bellman-Ford or Dijkstra or anything. Okay? And that's usually based on minimum cost or shortest path. Okay? طيب. We have to support some autonomous system to autonomous system communication, right? So between the autonomous systems, we have بقى highways بقى كده. يعني we can consider them as highways بقى. So we have one city here, and we have a highway to connect all cities together. ماشي? This is through what we call autonomous system routing. So that requires different types of routing techniques and protocols. Okay? So here we have a dominant protocol. حد فاكر كان اسمه ايه؟ ISIS. لا ISIS ده كان تبع ال OSPF، ده كان link state routing protocol. لا كان link state routing protocol. الثاني كان اسمه border gateway protocol. So border gateway protocol is the predominant بنسميهم exterior routing protocols. فدول بنسميهم interior routing protocols على اساس ان هم internal to the autonomous system. Border gateway is the main example when it comes to exterior routing protocol. ماشي؟ Exterior routing protocols they work differently from interior routing protocols, and usually they are not based on shortest path. they are not based mainly on shortest path. They are dominated by policies and regulations. يعني for example, if I have بقى مثلا autonomous system here, ماشي, I may have another highway كده. Okay. So if I have a destination here X مثلا, okay, and I need to send to X, I don't necessarily have to go through the shortest path اللي هي from me to X. I don't have to do that. I may have to go like this just because of the fact, يعني طبعا there is an autonomous system here, just because of the fact that I have service level agreement with this particular service provider. Like مثلا أنا I need to مثلا from Qatar I need to send مثلا إيه some communication traffic to China. Okay, so I may have to go through Vodafone in Europe, صح? I may have to go through AT&T in the US, okay? Or I may have to go through XYZ in Singapore, مثلا. Okay? In some cases بقى, I may actually have to go through AT&T in US to go to China. Why? Of course, this is not the shortest path, right? Why? Because I have certain agreements, right, with AT&T that the policy says that if you want to send traffic to China, you have to go through me. Okay? So this is bad, unlike خالص the mindset of interior. So within your infrastructure اعمل اللي انت عايزه. يعني go shortest path اعمل اللي انت عايزه. But when it comes to domain communication, that's usually governed by some policies and regulations which are بقى ايه يعني complicated, and they have some legal binding and so on. So you may not be able to go through a shortest path easily. يعني بعض الحاجات دي بتبقى ليها بقى قرارات سياسية مثلا يعني. خلاص يعني when you go to China you have to go through me. That's it. كده يعني. ماشي؟ So exterior routing protocols usually are dominated by policies and regulations, not necessarily by shortest path. ماشي؟ طيب, so the main thing here is that for each autonomous system I have a designated gateway. This is very important. I have designated gateway or maybe more than one, okay, that connects me to the other autonomous systems, right? So see how this happens. So this autonomous system 1 is connected to autonomous system 3 through this link, which is connected with router 1C. So router 1C is in that case the gateway that runs the border gateway protocol. So border gateway protocol runs on this router, okay, to connect this autonomous system with autonomous system 3. Similarly, 1B connects me to autonomous system 2, right? Type. So for every single router, whether it's a border gateway or it's an interior router, okay, they have the routing table which is fed from both, right? From intra-autonomous system routing algorithm like مثلا RIB أو OSPF والكلام ده. And they also have some entries from the inter-autonomous system routing protocol like border gateway protocol, right? Why? Because 1D needs to know that in order to go to a destination X, okay, so 1D da is a router, right? This router receives a packet with destination X, okay? How do I send this packet? I need to know, right? So this destination happens to be outside my autonomous system. هتقول لي لا ما ينفعش. This is allowed on the internet. Any router can receive a packet with any destination address, صح? Right? So that's allowed. That's possible, right? So 1D needs to know how to route this packet to destination X. Destination X is a network طبعا. ماشي? So it needs to know بقى whether I need to go through 1C to go to autonomous system to reach X, or I need to go to 1B, which takes me to autonomous system 2 to go to X. These are the two choices that I have. So I need to know now whether I should send to 1C or 1B. Okay, so that's known by the border gateway protocol, not by REP or OSPF. ماشي؟ تمام؟ Any questions؟ ماشي، الناس نايمة النهارده شوية مش عارف ليه. البي جي بي اصلا لا يعني هناخد نبذه عنه يعني مش هناخده بالتفصيل يعني عايز تاخده بالتفصيل طيب so الانتر autonomous system tasks so this is what I just explained, so there is nothing new in here. So suppose router in one in autonomous system 1 like 1D مثلا receives a datagram destined outside, let's say to somewhere here, lower X. Router should forward packet to gateway, but which one? This is what I was just explaining. Should I go through 1C in order to go to autonomous system 3 to reach to this network? Or should I go to 1B, which takes me to autonomous system 2, which will logically get me to the other part of the internet? So we need to know that. So that information is known through border gateway protocol. It's not known by REP or OSPF or something like this, okay? So we need to learn and propagate this information, and that's through what we call border gateway protocol. So this example here explains or reiterates on this. So suppose autonomous system learns that subnet X is reachable via autonomous system 3. So what will happen is that the information about X will propagate through border gateway protocol, right? And then it will go to here, and then again through border gateway protocol it will reach to 1C. So 1C will know this information that in order to go to X, I need to go through autonomous system 3, so I will forward the data to 3A, right? And 1C in turn will propagate this information to all other routers internally. Okay, so this information has to propagate. And of course, while doing this, they use route summarization. So again, for scalability issues, I don't have to really, because here there are multiple nodes and destinations, as we can imagine, right? But as we propagate this information, one job that border gateway does is that it actually summarizes. So, for example, the range of IP addresses, مثلا, in a certain area has a certain prefix, right? Okay, so I need to only propagate that prefix. So what I need to know is that any address in that range, I need to send to 1C. Okay, so they use a route summarization in order to save on the space of the route propagation, right? So that's known. Okay, so in that case, router 1D determines from the intra autonomous system routing information that its interface I is the last coast path to 1C. So it knows exactly how to reach to 1C through interior gateway routing protocols. But it knows that it needs to reach to X, right, through the exterior gateway routing protocol, border gateway routing protocol, and it needs to know that it needs to send to 1C in order to reach to X. So again, it uses this interface, interface I, next hub to reach to 1C. Okay. So this is a clear case, because again, X is only reachable from a specific autonomous system. But again, the internet is highly complex. So I may have, again, different ways to go to X, right? I may have different ways to go to X through different autonomous systems. So I need to have a way to know which one I should choose, right? So they use a combination of policy-based and shortest path-based combination to reach to the final destination. So in this example, we have multiple ways to go to X. So I can send to 1B, which will take me to autonomous system 2, and I will reach to X. Or I can send to 1C, right, which will take me to autonomous system 3, and I will reach to X. So which one I should choose? Which one I should choose, right? So in that case, you have possible choices. Some possible choices will be policy-based. So for example, if you have a policy that says that in order to go to X, you have to reach it through autonomous system 3, right? So in that case, خلاص, the policy dominates. خلاص, the policy dominates. So you have to send to X through autonomous system 3, which means that you have to send to 1C. Even, imagine here, مثلا ممكن يكون the distance to 1C here is 4, and the distance to 1B, the distance to 1C here is 4, and the distance to 1B is 1, right? And this is May 5, مثلا. Okay? So in that case, I can reach to X through 1B, which will take me through autonomous system 2, and I will reach to X. Or I can send to 1C, right, which will take me to autonomous system 3 to X. صح? I have both choices. I can do either. صح? But the policy says that you have to send to X through autonomous system 3. Why? Because this service provider you have certain agreement with this service provider to route all traffic to China through that service provider. Okay, so the policy dominates, and I have to send, even if the cost here is high, right? So the cost to 1C is higher compared to the cost to 1B, right? But the policy dominates in that case. خلاص. Okay? طيب. If I don't have such policy, or in other words, I have service level agreement both with this service provider or this service provider to reach to X. So I have both choices. Okay? So in that case, so the policy itself allows you to do both. So in that case, you may resort to the other level of calculating shortest path. اللي هو, should I go to 1C or should I go to 1B? So in that case, you may actually use the shortest path algorithm internally and say, okay, so I can go through 1B because 1B is the shortest path. أيوة. Yeah, so that's a good question. That's a good question. So this assumes that, of course, the distance between 1B and X and the distance between 1C and X is similar. It's the same. Okay? Because sometimes what you say is right. Sometimes I actually also take into consideration the amount of cost I need to incur or to pay through to reach to X from each service provider. Okay? So the policy dominates, of course, but in some cases also I use some path cost even externally. Right? But the assumption here is that this cost is similar from 1B or from 1C. Okay? So in that case, you can use the shortest path internally, right? And in fact, for a border gateway protocol, it maintains the entire path. It maintains from X to autonomous system 2 to autonomous system X to autonomous system 1. So it maintains the entire path. Okay? So, and they put this in the routing table. They put the entire path in the routing table. Okay? Right. So, but actually the dominant part is usually for border gateway protocol is as I said, policy, is the policy. Okay? So if the policy exists, then policy dominates, regardless of the course of the path. خلاص. ماشي؟ From 1D to 1B. لا ما of course بقى this what you are saying depends on بقى interior gateway, interior بقى routing protocol. Interior routing protocol knows that this cost is 4, بينما this cost is 6. So that scenario will not happen, of course, because of the fact that the distance between 1B and 1C, 4, is shortest, right? So that scenario will not happen. Okay, but the scenario that may happen is that either I go through 1B to this autonomous system or 1C to this autonomous system. So that I have some flexibility to do this, right? And if the flexibility is not, if the flexibility exists on the exterior routing domain type, okay, then I can use shortest path internally to get to whatever بقى gateway that can allow me to reach to X faster, right, or with minimum cost. Okay. Unless there is some kind of policy that exists, in that case, I resort to using the policy regardless of the shortest path. So we call it hot potato routing. The hot potato routing is combines the interior routing concept اللي هو based على shortest path with the external policy based routing. So here so use routing information from the intra-autonomous system routing protocol to determine cost for the least cost path, whether to go to 1B or 1C, as we said. Hot potato routing may choose the gateway that has the smallest least cost in that case. So first here, so we learn from the inter-autonomous system protocol that subnet X is reachable via multiple gateways. So if I have the case that X is reachable through multiple gateways, then we either use policy-based or we use the shortest path. So hot potato routing will check first the policy. If the policy says that you can reach from either gateway, then it kicks the shortest path interior routing protocol to calculate the shortest path to whichever path that has the minimum cost, using by link state or distant vector. Okay. Okay. Any questions so far? So this is hierarchical. So again, the motivation behind the hierarchical protocol was a scalability and the administrative authority through the control of internet service providers to their internal infrastructure. So they need to have control in the internal infrastructure that they have, in which case we resort to using hierarchical routing, which supports the interior routing protocols using REP, OSPF, or IGRP, or whatever, which runs internally, which maintains the scalability because the route updates will run in a single domain in that case, and use exterior routing protocols like BGP or border gateway protocol to maintain the inter-autonomous system routing. Type. Very quickly بقى we'll cover this part only. طبعا this part is not new, but we'll cover it يعني quickly كده يعني, and then we can break. أو ممكن حتى نبريك دلوقتي. So very quickly يعني supposedly we have covered this through other courses, but we'll go through it very quickly. So as we said, we divide routing protocols into interior gateway routing protocols, which include routing protocols like REP, OSPF, IGRP. IGRP is called Cisco proprietary, but it's a standard now. So Cisco pushed for it to become a standard, and now it's a standard. So we'll take one example from distant vector routing techniques, which is a REP, and we'll take one example from link state, which is OSPF, and we'll take one example from exterior routing protocols, which is BGP. So we'll talk about REP first. Routing information protocol is actually standardized in 1982, and it's a distant vector routing protocol, of course, which means that it uses a Bellman-4. It uses Bellman-4 technique. The distant matrix is simply the number of hops, and as we said, the maximum number of hops is 15. 16 is considered infinity. Okay. So if this is the routing table for router A, okay. So if I need to go to U here, so that's a local network. A local network, which means it's one hop. So the price for all these nodes is by default 1. The price on each link is 1. Regardless of the bandwidth, regardless of the delay, regardless of... So REP uses a very simplistic way for calculating the shortest path through number of hops. That's it. ماشي? So if I need to go to U, it's 1 hop directly. If I need to go to V, it's 2 hops. If I need to go to W, it's 2 hops, and so on. If I need to go to X, it's 3 hops, and so on. طبعا when I need to go to X, it's 3 hop. I have to say what is the next hop. So the next hop here is either B or C, right? صح? So when I go to X, I can go through B or I can go through C, صح? And both of them will be the same thing. طيب, if I have بالمناسبة بقى, if I have a situation like this, rep uses anyone. Rep uses it because the cost is from B or from C is the same, right? So if the cost for 2 potential paths is the same, rep uses only one of them. Okay, it puts one of them in the routing table. So here the next hub will be either C or B. Okay, why am I stressing on this? Because for OSPF it actually uses B and C. It stores both. Okay, it stores both, and we'll see why. Type. So distant vector exchanged neighbors every 30 seconds. Okay, so it's periodic. It supports periodic updates, and all the updates, they happen every 30 seconds. There is an exception to this that we talked about in network 2, but it's not important. So each advertisement we list up to 25 destinations. هتقولي, what if I have more than 25 destinations? Then we report it through multiple messages. Yes. So each message contains 25 distances. Okay? Up to 25 distances. That's the protocol design. That's how it's designed. ماشي? If I have 75 different destinations I need to report, then I have to send 3 separate messages. And the domain for each message is 1 hub. يعني it reaches to all the neighbors only. ماشي? It's not flooding. It's 1 hub. ماشي? So that's يعني a quick example. So if I need to go to, if this is the routing table for D, so here it's D, right? So D calculates the distance to each of the different destinations. So if I need to go to W, if I need to go to Y, Z, and so on. So if I need to go to Z, for example, I have to send it to B. So B is the next hub, and the cost is 7. Of course, 1, 2, and then there is like some 5 different hubs here. Imagine. So that's normal. So if, for example, D now receives the vector of distances from A, okay, and these vector of distances contains the route entries inside the routing table of A, and that happens to have the distance W. The distance W is 1 hub, the distance X is 1 hub, and the distance to Z is 4. And the distance to Z is through C, which means now that A can reach to Z through C, ماشي? And now it's only 4 hubs. Okay? Of course, in that case, D needs to know about this. So D will say, okay, so what interest do I have? And it compares using the Bellman-Ford, as we said. So it says, okay, so if I need to go to route to Z, I either route to B and the cost will be 7, or I route to A, and in that case the cost would be 5. اللي هي 1 plus 4. Of course 5 is less, so it updates its route entry that now to reach to Z, I need to go to A instead of B, and the cost will be 5 and not 7. It's very simple, yeah. Very simple. Okay? So this is how we calculate or we estimate these distances accumulatively. Of course, we talked about the possible issues related to count to infinity and so on and so forth, and we have some approach to solve it, which is the Poisson reverse. In case of failure, or in case of some change of lengths, as we said, if no advertisement heard, so we assume that we have to receive route updates from the nodes next to me, okay, every 30 seconds. So after 6 different rounds, which means 180 seconds, I did not receive any route updates from a particular router. Okay, so in that case, rep considers that the link to this router is disconnected. That's how we discuss. So we set the cost of this link between me and the router to infinity, and now we have to report it. طبعا report it معناها we have to go through اللي هو الايه bad news travel slow, but we need to be smart, so we use a Poisson reverse. So in that case, we have to use Poisson reverse to report the information about this cost, which is now infinity. أو infinity for rep طبعا اللي هي 16 يعني. ماشي؟ طيب. Interestingly بقى, rep, in order to send route updates, we have the choice to send these route updates بالنهاية هي messages. ماشي؟ So I need to use some kind of encapsulation to these messages. Okay? So rep encapsulates this message using UDP transport protocol. And that entails the fact that, of course, these messages are unreliable. But there is a reason for this. There is a clear reason for this. Rep may, in fact, support multicast to send to its neighbors. Okay? So you can use multicast to send route updates to all your neighbors, okay, in one transmission. صح كده? And as we said before, if we use TCP, we'll have reliability, صح. But TCP is very bad when it comes to multicast communication. هتفكر ليه؟
It needs to establish connection with every node before it sends and make sure that the link is
صح.
live, which will consume so much time and
هي not only that كمان يعني أنت when you send a segment to all your neighbors, okay, you have to expect مثلا ان انت you have to receive acknowledgements. So when do you decide that you received acknowledgement from all of them? That's a tricky situation. So should I consider receiving the acknowledgement from one that the packet has been delivered successfully, or I have to receive from all of them or part of them? Okay, so the concept of acknowledgement makes دايما المulticast very tricky. That's why TCP is not very desirable when it comes to multicast transmission. Okay, that's why none of the routing protocols, by the way, at least that I know of يعني, it uses TCP for, except border gateway. نتكلم على border gateway because it doesn't use multicast in that case. It actually reports between autonomous systems, so it establishes TCP. But interior routing protocols, they never use TCP because they support or they may support multicast to send route updates. مفهومة الحتة دي ولا؟ So the advertisement through UDP is sent periodically, and UDP معناها إيه؟ No reliability. ماشي؟ طيب. This is a يعني for rep is distant vector routing protocol. For OSPF بقى open shortest path trace. طبعا open هنا معناها publicly بس doesn't matter يعني. open معناها publicly available معناها it's standard وبتاع. طيب it uses that link state which means that it maintains بقى ايه link state database with supports link state packet dissemination through flooding. كل الكلام اللي احنا اتكلمنا عليه. ماشي؟ I have topology map at each node, topology map, which means link state database at every single router, and then we use Dijkstra to a type. OSPF advertisement carries one entry per neighbor, and it actually sends each packet يعني, or each link state packet will have at least the link state for one edge, and it sends it to flooding to the entire network. Advertisement here disseminated in the entire not by the internet, autonomous system. And as we will see يعني there is حتى يعني subdomain هنتكلم عليه دلوقتي. So OSPF messages directly are sent over IP. يعني ما فيش حتى يعني it doesn't use TCP and it doesn't use UDP because actually ما هو IP نفسه is unreliable. ما هو IP is best effort طبعا. IP نفسه best effort. Okay. Why do we need the UDP? عشان port. We don't need ports for updates. For route updates, we don't need ports. So in that case, we send the messages through directly through IP, which means that برضو طبعا IP is unreliable كل حاجة. And طبعا IP supports multicast. It's possible to have multicast. Again, because we don't require any acknowledgement. For IP, there is no acknowledgement. But we can still use it for multicast. اتفضل.
The update message can be lost, right?
طبعا. ما هو supposedly ايه؟
The protocol still works.
طبعا لأن هو يعني supposedly even if the error happens, it rarely happens, and as long as it doesn't happen 6 times repeatedly. Because if it happens 6 times repeatedly, then we consider this link as a failure. وخلاص the link is disconnected. But this is unlikely. In fact, even one single error is very unlikely to happen. طيب. OSPF بقى built برضو on lessons learned from other routing protocols like REP. So REP at the beginning did not support any kind of security, and as you can imagine طبعا. The effect of a predator router مثلا or a router that's compromised and it sends route updates, especially for distant vector, as we said, it's less robust when it comes to يعني reporting wrong information about links, and the error propagates and stuff like that. So OSPF did not want to take any chances, so they support security from version 1. They support security, which means that the routers, they establish some kind of authentication. We'll talk about this by next semester. So there is also multiple same coast path allowed. اللي هو بقى اللي احنا كنا بنتكلم عليه من شوية. يعني for REP قلنا when I have a certain source and a certain destination and I can reach to the destination from 2 possible paths and the cost is the same, REP uses 1, right? OSPF maintains both. ليه بقى؟ طبعا يعني through different interfaces يعني. Why do you think يعني OSPF may maintain both routes in the routing table? Why? هو عايز كده هو حر بس يعني why do you think يعني I may have this overhead of maintaining both. بس باك اب انت قلتي باك اب صح؟ That's one reason صح؟ مظبوط سوري انا ما سمعتهاش كويس. صح صح يعني for backup يعني for failures, for potential failures for backup. بس حتى لو ما فيش failure, I may in fact maintain both routes. أيوة. لا ما هو link state معناها I have link state database, I run Dijkstra calculates shortest path, صح, shortest path tree as we said, right? But shortest path tree دلوقتي tells me that you have multiple routes with the same cost, okay? So either you say, okay, so I'll take one, or you maintain both. OSPF maintains both. ليه بقى؟ عشان يعني طبعا backup is one reason, and the other reason is load balancing. We call it load balancing. حد عارف اللود balancing؟ حد عارف اللود balancing؟ If I maintain both routes, I may in fact choose to send some packets here and some packets here. I have the choice to use both routes concurrently at the same time. Hence, reduce the load. Okay? فبيسموه بقى traffic diversity. You will call this load balancing. ماشي؟ I may in fact use both routes at the same time. Not only that, but one extra complexity. For each link, multiple cost metrics for different type of service. يعني ازاي؟ يعني دلوقتي there is a link مثلا to reach to D through satellite. Okay, that link, okay, will have the same link and the same technology through satellite. It has two different costs. Cost for a type of service if I have satellite link cost set to low for best effort. So if I have an application that's best effort and supports best effort, يعني مثلا زي browsing مثلا واحد بيعمل browsing ولا حاجة. So in that case, the satellite cost will be low, that encourages you or encourages the routing protocol to use this link for this particular application. Because the cost is low, which means that if I select satellite communication for an application that is tolerant and it supports best effort, like مثلا web browsing ولا حاجة, that's perfectly fine. ماشي? If I have a real-time application for that satellite communication, the cost increases high. So in the routing table, I maintain two entries for different type of service. OSPF supports that. Okay? So for a type of service which is best effort, the cost will be low. For a type of service that's real-time streaming, the cost will be high. In that case, of course, the Dijkstra's algorithm will be discouraged to use the satellite communication for real time, but will be encouraged to use it for best effort applications or applications that does not require specific quality of service. OSPF supports that. I'm not saying that you have to use it, that's a feature. OSPF supports that, or at least it says that it's valid. So in the routing table, you may have two routing entries for the same link with different costs, but different type of service. OSPF uses or supports multicast OSPF, which supports, again, not بقى multicast route updates, but multicast communication. طبعا كان في section اللي هو multicast broadcast and multicast routing, but we'll not get the chance to cover it. In addition to that, we have what we call بقى hierarchical OSPF. Hierarchical OSPF, مش hierarchical routing, لا يعني احنا OSPF is an interior routing protocol, بس which works inside one autonomous system. So inside one autonomous system, we have hierarchical OSPF. Okay, why is this? So OSPF now supports the concept of area. And again, we talked about this in network 2, if you remember, yani. لما كنا بنتكلم عن administrative distance وقلنا ان OSPF in addition to the administrative distance it uses the concept of area number. So in addition to administrative it uses a area number. Okay? So the reason for this is that OSPF supports very large autonomous system infrastructure. So if you have very large autonomous system, it subdivides this autonomous system into what we call areas. Areas is like a subdomain inside the autonomous system. Why do we do this? Because again, link state is actually reported through flooding. So the link state gets flooded. So in that case, you can flood the link states inside an area, but you have to report also the link states to other areas as well. But this happens through what we call area border routers. So area border router kind of summarizes the link state routing to other areas. So before it sends and floods the link states, it may actually summarize these link states to one link, which means that if you want to send to anything here, send through me and I will send it to this area. If you want to send to anything here, send to me and I will send to this area. So it kind of subdivides the autonomous system into subdomains. We call them an area. So the way that we categorize or the way that we organize these areas is through, we have area 1, area 2, and we have the backbone area. The backbone area is the designated area which connects this autonomous system to other autonomous systems. So here I have a autonomous systems back. So the backbone connects this autonomous system to the other autonomous system. So we have boundary router. The boundary router here is the gateway that connects this autonomous system to other autonomous systems. So we have boundary router and we have area border router. The area border router is a member of the backbone and it connects this backbone to one area. واضح الفرق؟ ماشي؟ So there is backbone router and there is internal routers. So these are terminology definitions which OSPF uses, and the concept of area makes OSPF even more scalable through this hierarchical nature or hierarchical design, okay? Through the concept of areas. Areas are just subdomains inside the autonomous system. ماشي? So when I send the route updates, I have to report the area number. Why? Because it may go to the area border router, and the area border router decides to summarize the link states into one before it sends it to other areas. Okay? طيب, hierarchical OSPF, it uses a two-level hierarchy which supports the local area and the backbone, and the link state advertisement only in an area, right? So when it comes to reporting to other areas, the area border router can in fact use some kind of summarized information to send it to the other area. And there is area border router which summarizes again the distances, right, to the different networks. There is the backbone router, and there is the border router again is the one that connects this autonomous system to other autonomous systems. Any questions? So these are the definitions that OSPF uses. Again, there is lots of details related to that we will not. Last one is Border Gateway Protocol, and Border Gateway Protocol is the de facto standard when it comes to inter-domain routing protocols. It's the predominant exterior routing protocol on the internet. Okay. So BGP provides autonomous system the means to اللي هو في عندي exterior border gateway protocol which is used بقى to learn اللي هي الهايويز دي. Exterior border gateway protocol is the one بقى that is actually more dominantly it uses بقى policies, regulations and stuff like that to know how to learn the reachability of different networks through other autonomous systems or other internet service providers. Interior Border Gateway Protocol is the one that reports this reachability to all routers inside the autonomous system. واضح الفرق؟ So propagates this reachability information to all autonomous system internal routers. I still need that because each router now maintains information coming from BGP with the information coming from the interior routing protocols in the routing table. ماشي؟ Determine بقى good route through بقى اللي hot potato routing بقى زي ما احنا قلنا. If there is a policy, if there is a certain policy, I have to abide by the policy. If there is no policy, then I can use بقى shortest path and so on. ماشي؟ So BGP sessions بقى in that case, I establish BGP sessions between the border gateways اللي هي ايه designated for each autonomous system, and in that case بقى we establish TCP bidirectional communication between these border gateways. So that's the only يعني example where TCP is used to report, but not only بقى not the route updates, the internal route updates, but in that case اللي هي external path reachability information for the external or inter-domain communication. So advertising paths to different destination networks prefixes exchanged over semi-permanent TCP connections, as we said. ماشي? When autonomous system 3 advertises a prefix to AS1, AS3 promises it will forward the datagram to this prefix, which means that AS3, okay, reports a certain reachability to a specific network to AS1. This means that we have a service level agreement, and AS3 now promises AS1 that it will send any packet for a destination in this range of IP addresses through AS3. Okay, so in that case, the policy allows. There is a policy or service level agreement between AS3 and AS1 to route the traffic to a specific network through AS3. So AS3 بقى may aggregate all these prefixes, as we said, through route summarization. So here I report the advertisement for the entire IP address range in one route update. ماشي? So the basics here is that using the exterior border gateway session between 3A and 1C here, so we have exterior border gateway session and we have interior border gateway session. This interior border gateway session is the dotted one, which is internal. The exterior one is the one that uses, as we said, TCP, and it reports the reachability from one autonomous system to another. So in that case, 1C uses the interior border gateway protocol to distribute these prefixes through the iBGP session to all the internal routers. Okay. So طبعا هنا بيقول لك 1B can then re-advertise the new reachability information to autonomous system 2. That's again, this is according to the policy. If there is a policy that allows the traffic from AS2 to go all the way to this through مثلا AS1, then so 1B will report that to autonomous system 2. Okay, so that all depends on the policy. So the last thing here is that these advertised prefixes includes the BGP attributes. So any route is in fact a prefix. A prefix طبعا represents range of IPs. So if you want to route to range of IPs, then this prefix will represent all this range of IPs and certain attributes. These attributes بقى, they contain AS path. This is very important. The AS path here may in fact contain all the ASs. All the ASs, so all the autonomous systems that this route advertisement went through. So here, this AS path is one of the attributes, and it may say, okay, so this is coming from AS مثلا 4 through AS 7 through AS10 through AS5. Okay, so this whole path is maintained through the route advertisement. Okay, for eBGP. So that's one of the attributes اللي هو ال AS path. And طبعا اللي ايه النكست هاب. النكست هاب اللي هو ايه؟ So if I want to reach to that autonomous system, I have to go through this next hub. So based on that path, why do I have to store the entire path? Because then if an autonomous system wants to send to a specific destination through this whole path, it may have to check the policies that it has with every single one of them. Okay? Does it have a policy to really send through these autonomous systems or not? Okay? And also, this AS path may be used for shortest path. If I have reachability from different autonomous systems, I may actually use the AS path to kind of calculate whether if I need to go through this autonomous system is shorter or this autonomous system is shorter. ماشي كده؟ طيب gateway router receiving route advertisement uses بقى ايه policy, and based on the policy then it says okay, so I can route through this path because I have policies with every single autonomous system in this whole path. Okay, or if I have multiple paths of them, which one is shorter, and I may have to take that path. Okay. So this is the criteria for selection. The shortest AS path, okay. The closest next hub when it comes to if I have next hub اللي هو بقى gateway. If I have a specific like multiple path, each one through a specific gateway to reach to different autonomous system. So either I take the shortest path or طبعا the policy. If the policy exists, it dominates. If the policy exists, it dominates. If the policy does not exist, which means that you have flexibility to go through multiple autonomous systems as you wish, in that case, we calculate the shortest autonomous system path. So I have a path that says AS3, then AS5, then ASX. Or another one goes through AS4 and then ASX. Okay, so these are two potential paths, two potential autonomous system paths I can go through. The policy allows either of them, allows both. Okay, so in that case I may say no, this one is shorter. ماشي? Or if I have both of them using the same AS path, or يعني the same cost for the AS path. So one is AS4 ASX and the other one is AS10 ASX, which means that autonomous system path in terms of cost is pretty much the same, right? So in that case I'll go to the next level. AS4, I can reach it through a specific gateway internal inside the يعني مثلا مش عارف انتوا حاسين البتاع ولا. This is the gateway that gets me to AS4. This is the gateway that gets me to AS10. Both of them allow me to reach to the same destination, right? So if the AS path is the same, so it's only like one path to get to the autonomous system here, or one path to get to the autonomous system here, and it seems that the autonomous system path is the same in terms of cost. Okay, so in that case, I have a router here. So in that case, I can see which one is the shortest. So here, مثلا, the cost is 3 and here is 10. So in that case, I will go through this. So first the policy, second the autonomous system path. Okay, if the autonomous system path is in terms of cost is the same, then I go through by shortest path. ماشي? So these are the levels. I may have different criteria بقى زي ايه بقى. I may have to go by type of service. I may have to go through other criteria as well, depending on the type of service of the application and so on. So these are the messages, but these are the messages, details about how we report the اللي هو ال EBGP advertisement. These are the messages. You don't have to memorize the messages. يعني ماشي. I think we can. So this talks about dual home اللي هي أصلا there's nothing new here. الدول home اللي هي إيه؟ If يعني I have A and B and C provider routers, and here dual home معناها إن A has reachability to X through B and C. Okay, so in that case, as I said, we have to use the policy to calculate or to choose which service provider I need to use in order to reach to X. So there is nothing new here actually. I think we'll stop here. يعني كل الحاجات we cover. هنا بس احنا بنقول ايه؟ why we have the difference between the intra and inter autonomous system routing, as we said. اللي هو فكرة ال hierarchical routing in general. The policy, the inter autonomous system admin wants to control over how their traffic can be controlled. This is what we talked about, اللي هو administrative authority. So a specific entity, مثلا like Ooredoo or Vodafone, they may have to, or they want to have control over their infrastructure. So in that case, they can use any intra-autonomous system routing protocol inside their infrastructure. They may use RIP or OSPF or EIGRP or something like this. And for scalability, we have to use the concept of hierarchical routing through exterior and interior gateway or interior routing protocols. So in that case, we have the inter-domain routing or inter-autonomous system routing. So that affects طبعا the performance. So the intra-autonomous system can focus on performance in terms of shortest path and so on. صح? So, and the inter-autonomous system, it focuses on policies and regulations, to enforce policies and regulations to maintain the service level agreements with the different service providers on the internet. So, يعني again, there is nothing new here. We talked about the motivation behind the hierarchical routing. So that, I think that's it. So this last part will not be covered. Will not cover it. So, any questions?